Hi everyone, my name is Javier Zamora and today I'm going to be presenting Lab 2 for Physics 2211, which is the motion of a falling object. So the purpose of this lab was to observe the motion of an object that is dropped from rest and to expand my knowledge on gravitational and drag forces by creating and comparing computational models. So a preview of my results is that the gravitation and drag model is more accurate than the gravitation model. Yeah. So to start off, we're going to review some of the important concepts used in this lab. First, we have Newton's second law, which is the change in momentum over the change in time. Then we have the gravitational force, which is also the free fall. This force pulls objects with mass towards each other, and that's the formula. And finally, the drag force is directly proportional to a constant times the velocity squared of that same object. So for this experiment, I dropped the cap of a marker, which in this case would be the system, and the surroundings would be the Earth, which had the weight force acting on the marker cap, and the surrounding would also have the drag force acting upon the object. So after recording everything in the tracker software, you can see the position for the object on the graph on the bottom shows a parabolic shape. So next I did this computational model that showed the effects of just weight and no drag force on the marker, which is in the GlowScript code, where I set the initial position of the marker as 0.821, which was indicated by the tape measure behind the marker, and no drag forces, so that B would equal 0. In this case, B would be the proportionality constant of the drag force itself, and the only force acting on the marker would be just the weight force, which is the mass of the ball times G times J hat. Okay, so here are both graphs of the tracker video versus a computational model that includes no drag force, and as you can see, they are very similar. The computational model with drag included the drag force that was calculated by using B, and using the trial and error by the magnitude of velocity squared times J hat to convert it back to a vector. We can both add the weight and the drag forces to obtain the net force. Here is the three graphs I put together, and there's almost no noticeable difference between any of these three graphs, so we can conclude that all the graphs are extremely similar, and this is due to the fact that there's a very little drag force acting on the marker cap because the cap has almost no surface area for the air to act on it. Nevertheless, both the computational models with the drag and the tracker video are slightly less steep than the computational model that had no drag force acting upon it, and this is probably because the drag force acting on the cap makes the acceleration and the velocity slightly smaller than the one that, and this is probably because the drag force that acts on the marker cap makes the acceleration and velocity slightly smaller than the one that had no drag force acting upon it. Also, a few sources of error in this lab could be the human error when I selected the positions on the tracker software, as well as the distorted video from the angle that the phone was when I recorded the video. So what does it mean? What would happen when the computational model shows the terminal velocity? And what is exactly the terminal velocity? That would be the velocity at which drag force becomes as big enough to be equal and negative and opposite to the weight force. So this would mean that the net force would be equal to 0, and that the object is moving at constant velocity. So what if the market cap had been thrown downwards at initial velocity? That would still make no difference, and the object will still have the same terminal velocity as seen on the graph below. The velocities are going to curve up until it becomes a horizontal line, And we have to remember that terminal velocity depends on their mass and drag.